Ensoftec has developed a series of videos for the selection and design of stormwater facilities for land disturbance projects. In this video, I shall show you the design of infiltration facilities, both small-scale infiltration trenches and conventional infiltration basins, using SWMSOFTVA. Virginia Department of Conservation and Recreation, or DCR Specification Number 8 gives a complete description of these facilities, their performance and criteria for design, their feasibility and design applications, regional and special case design adaptations, their construction and maintenance. The pictures and tables shown here are from these specifications. Table 8.1 gives the summary of stormwater functions provided by infiltration practices. You will notice that infiltration practices achieve a high degree of runoff volume reduction as well as nutrient removal. Hydrologic soil group A or B, soils provide greatest recharge and infiltration rates. They are therefore considered as primary locations for infiltration practices. These devices are ideal to treat runoff from medium and highly impervious sites. Table 8.2 gives the infiltration design guidelines. There are two levels of design, the baseline design, level 1, or an enhanced design, level 2. While a level 1 design uses at least 2 forms of pre-treatment, a level 2 design requires at least 3 forms of pre-treatment. The maximum impervious area that can be treated at an infiltration trench is half an acre and by an infiltration basin is 2 acres. The bottom of infiltration practices should be at least 2 feet above the seasonally high groundwater table. I now open the project, which we had set up in video 3. BMP2 of Outfall 4 is an infiltration basin. I shall use this example to demonstrate the design steps. I go to File, Design BMP Facility. This opens the infiltration basin worksheet. You will note that the percent impervious cover and the required water quality treatment volume fields are already populated in the screen. Adequate pre-treatment is needed to prevent premature filter clogging and extend the life of the filter media. These basins are usually sized using the Camp-Hazen equation. Pre-treatment cells must be sized to accommodate at least 25% of the total treatment volume, to keep sediment and vegetation out of the infiltration cell. I enter the infiltration rate for native soil in the proposed infiltration area. The default minimum value is 0.54 inch per hour. I enter bottom and top elevations of the pre-treatment cell, and click on Compute Volume. This opens the Basin Volume Computations worksheet. This sheet has 6 columns and 12 rows. You will notice that bottom elevation of the pre-treatment cell is already populated in the first row. The top elevation of the pre-treatment cell is also populated. I need to fill the first 2 columns starting from the lowest bed elevation and surface area at that elevation in square feet. I start filling this data from the first row. I make sure that the elevations keep increasing as I move down each row. Also, as this is a basin, the areas should also increase as the elevation increases. An error message is displayed if the data is incorrect. While there are 12 rows to accommodate up to 11 feet of storage depth assuming that the incremental elevation is 1 foot, it is not necessary to fill in all the rows. I fill in areas and elevations up to the top of 4B. Having entered the incremental elevations and areas, I click the Compute button at the bottom. This will compute and populate all the remaining fields. Column 3 gives the average area in square feet between successive elevations. Column 4 gives the volume in cubic feet between successive elevations. Columns 5 and 6 give the cumulative volumes from the lowest bed elevation to final elevation, in cubic feet and in acre-feet respectively. You will also notice that the surface area and cumulative volume at the top elevation are also populated. I could always click on Clear button at the bottom, which will clear all the 6 columns. This will enable me to re-enter the first 2 columns and re-compute basin volumes. Exit will close this screen and puts me back to the previous screen. You will notice that the pre-treatment volume and area for the top elevation are populated. I click on the Design Pre-treatment. The program calculates the required pre-treatment volume and area and compares with the size provided. The remarks will show if the pre-treatment design is satisfactory or not. The required design volume, which is the total treatment volume reduced by the pre-treatment volume, is automatically populated. You will notice that default values are provided for some of the fields that follow. In order to reduce the potential for nuisance conditions, the maximum drawdown time for infiltration practices should be 24 hours to 48 hours. A default value of 0.4 is provided for the porosity of the trench material. The time to fill the infiltration facility is usually 2 hours. I enter bottom and top elevations of the infiltration basin, and click on Compute Volume. This opens the Basin Volume Computations worksheet. This sheet is similar to the pre-treatment volume computations worksheet with 6 columns and 12 rows. You will notice that bottom elevation of the treatment trench or basin is already populated in the first row. The given top elevation is also populated at the bottom. I need to fill the first 2 columns starting from the lowest bed elevation and surface area at that elevation in square feet. Unlike in the pre-treatment cell, infiltration basins are often designed for additional storage on the surface or in the subsurface storage volume, to accommodate larger storm volumes. I enter elevations and areas to the expected top of embankment. Having entered all the basin elevations and areas, I click the Compute button at the bottom. This will compute and populate all the remaining fields. Column 3 gives the average area in square feet between successive elevations. Column 4 gives the volume in cubic feet between successive elevations. Columns 5 and 6 give the cumulative volumes from the lowest bed elevation to final elevation, in cubic feet and in acre-feet respectively. You will also notice that the surface area and cumulative volume at the top of basin elevation are also populated. I could always click on Clear button at the bottom, which will clear all the 6 columns. This will enable me to re-enter the first 2 columns and recompute basin volumes. Exit will close this screen and puts me back to the previous screen. You will notice that the surface area and basin volume provided are populated. The required basin surface area is computed using the Darcy's Law as derived by the City of Austin, Texas, Environmental and Conservation Services Department. The surface area is a function of the treatment volume, the infiltration rate, the infiltration depth and the time for water to fill the infiltration facility. With these input values, the program calculates the maximum allowable depth for the facility, using equation 8.1 of DCR specification 8. After entering all the open fields in the treatment section, I click on the Design Treatment button. The program calculates the required infiltration trench area, and compares it with the area provided. The remarks will show if the design is satisfactory or not. I go to the top menu bar and click on File, Save. This will save all the data including the results. I now go to the top menu bar and click on File, Print. The print report, which is in Excel format, gives the results of analysis. Quantity control for infiltration basins is performed similar to extended detention ponds. They are designed to reduce the peak flow from 2-year and 10-year storms for channel protection, and pass 100-year storms safely. It is preferable to locate an ED pond, as a part of a hybrid system in the treatment drain, where the infiltration basin feeds to the extended detention storage facility. The program includes the design of outlets. To perform outlet analysis, I go to the top menu bar and click on File, Outlet Analysis. This opens the Outlet Analysis screen. You will notice that there are 2 sections here. To the left, you will notice Orifice Details, Spillway Details and Emergency Spillway Details. To the right, you will notice that the water quality volume required is already populated. I can select 24 hours or 36 hours from the pull-down list for extended detention storage time. I enter the maximum hydraulic head. There are 2 procedures to determine the orifice size, to hold the extended detention storage volume. The program uses the DCR method to average hydraulic head, which is the VDOT preferred method is given in the Virginia Stormwater Management Handbook, and gives the size of orifice in inches. This size is used in the orifice sizing to the left of this form. There are 3 types of orifices for the user to choose from. 2 circular shapes and 1 rectangular shape are given. The center line elevation of an orifice should be such that the invert of the orifice should be above the top of filter bed elevation. A checkbox is provided against each, for the user to select. Likewise, there are 3 types of spillways for the user to choose from. A side open riser, a circular riser and a rectangular V-dot standard SWM1 riser are available. There are 2 types of emergency spillways for the user to choose from, a broad crested weir and weir wall types are available. A checkbox is provided against each of the above for the user to select. I enter the data applicable for the proposed riser structure. I then go to the top menu bar and click on File, Save. This will save all the above data. Next, I go to the top menu bar and click on File, Print. The print report, which is in Excel format, gives the results including a staged discharge curve for the outflow. Infiltration basins are not designed as extended detention facilities. As such, the program does not perform any reservoir routing procedure. The program provides the inflow hydrographs for the post-project conditions only. For retrofit basins with pre-development site areas and inflows, the hydrographs for existing conditions are also generated. For the inflow hydrograph, the program uses the NRCS dimensionless unit hydrograph. In an event-based model such as the NRCS method, the rainfall hydrograph for the design rainfall event is based on the CN method and the application of the NRCS 24-hour rainfall distribution is well documented. I go to the top menu bar and click on File, Generate Hydrographs. Inflow hydrographs are generated for the 2-year, 10-year and 100-year design storm events. If I go to File, Summary Table, a new screen opens giving the drainage areas, pre- and post, rainfall depths and peak discharges for the 2-year, 10-year and 100-year design storm events. As a last step in the design of infiltration systems, I go to File, Perform Outlet Analysis. This opens the Outlet Analysis worksheet. You will notice Outlet Barrel Sizing worksheet to the left and Emergency Spillway Design to the right. The 10-year and the 100-year peak discharges are already populated in the form. I enter the outflow barrel details, its length, diameter, invert in, invert out and the barrel material type. I also enter the top of riser elevation. When I click on Compute, the program calculates the hydraulic head at the riser. The remarks field indicates if the water surface elevation in the riser is inside the riser or above the riser, indicating inlet control or outlet control. The barrel's size, slope or material can be adjusted to ensure that the water surface elevation is inside the riser. Now I enter the emergency spillway details, its length, width and the emergency spillway top elevation. I also enter the top of embankment and the required freeboard. When I click on Compute, the program calculates the head above the weir. The remarks field indicates if the freeboard is adequate or not. I then go to the top menu bar and click on File, Save. This will save all the above data. I go to the top menu bar and click on File, Print. The print report, which is in Excel format, gives the results of outlet analysis. This completes the design of infiltration systems.